In algorithms 2, can everyone see my screen, by the way?
Yep.
Okay, thank you. So in last hour, now that you're back from your break, this is going to be the last half an hour of workshop. And so now we're going to take up the exercise that I assigned during the algorithms 2 that you were supposed to work on during the break. Now, don't worry if you didn't get everything. Some of it is quite challenging, so that's okay if you missed something, and we're going to take that up right now. So I think I'm just going to take up these exercises one by one because they're kind of increasing in difficulty. So the first exercise is just for you to make an adjacency list by asking the user for the number of nodes and edges, and for each edge, the 2 nodes that they connect. So, okay, so the way I did this is, so I'm going to ask them for the number of nodes. So nodes is an input, how many nodes. So it's going to ask me how many nodes I want to input. And so I'm going to type in 12. And so this is the input I'm going to put into it. And if you're if you're curious, it's just this graph that I just pasted below. You'll recognize this from graph from the end of practice, the end of the first little activity that we did there. So I'm going to just reuse this same graph. In case you want the edges for this graph, I can also paste this input. These are the edge lists. These are the list of edges. Or actually, I think those are already pasted above. So, okay, so this is the graph I'm going to be referencing. So, whoops. Yeah, then I'm going to ask for the number of edges. So in this graph, there are 12 nodes and there are 12 edges. And for each of the edges, I'm going to ask them for the 2 nodes it connects. So first of all, I'm going to declare a list. So adjacency list, I'm going to start with an empty list for every single node. So remember that we have to do nodes plus 1 because 0 is a dummy node and the node 0 doesn't exist here. And it's important to note the difference between between this and something like this. Just because of how memory works and copies, this will actually not give you, or there's an extra set of brackets here. So this will not actually work very well because when you do this, whatever you do to one list, it's also going to be done to all the other lists that are the copies. So make sure you can define your visited lists like with multiplication like that, but when you're defining your adjacency list, make sure you're using list comprehension or something that achieves a similar result. Okay, so after I take in these 2 nodes, so I'm going to store them in variable A and variable B. So since I'm assuming these edges are undirected in this graph, so there's no arrows, so they can go both ways. So then I'm going to say A is a neighbor of B. So adjacency list at A is going to add the value of B. And the adjacency list at B is going to add the value of A. And I'm going to print this adjacency list just to show what it outputted. So actually, to not make it distracting, I'm going to comment out the rest of the program here, just so it won't output anything. Okay, so how many nodes? 12, 12, 4, 1, 4, 2, 4, 3, 4, 7, 5, 6, 6, 7, 7, 8, 8, 9, 12, 10, 7, 10. And finally, it wants us to enter 2 nodes because I have another thing down there that that's for exercise 3. So ignore that. Okay. So this is the adjacency list that we outputted right after we. Okay. see if I can copy this. Okay, so that worked. So this is the adjacency list that we constructed by doing this little process here. So just to review, we take here we're taking an edges and we're initializing adjacency lists. So it starts out as empty lists, and so here we're saying that B is a neighbor A, and here we're saying that A is a neighbor. This is one way you can construct an adjacency list or representation of the graph using input. So you take in the number of nodes and the number of edges. You loop through all the edges, and then you make sure that B is a neighbor of A and A is a neighbor of B when it's an undirected graph, of course. Okay, and so the result we get is this, which should look something similar to what we had before. So let me try to find that. Okay, so it should look something similar to this. Right, so this is the adjacency list you get if you analyze this graph. Okay, so on to, okay, so any questions about exercise 1? Okay, if you have questions at any point, feel free to ask. Oh, and someone mentioned that they don't have the link. So just in case anyone doesn't have the link, I'll just post it in chat again. This should be the link to the lesson. Okay, the lesson plan, I mean. Okay, so let's move on to exercise 2. So for exercise 2, I just asked you to try to implement DFS and DFS yourself and traverse the graph received from the input. And so this is actually, we already did this. We went over the implementation, but now we're just going to review it again to really make sure you understand the implementation. So I'm going to uncomment that. And so let's first look at our DFS. So I'm going to enter in the input real quick. Okay, so let's look at our DFS. So this is just indicating that we're starting from 1. And here we're initializing. And as soon as we arrive, mark here we're going to loop through its neighbors. Here we're making sure it's not visited yet. And finally, we can call the function again on that neighbor to go to. Okay, so this is our DFS. So when we arrive, we mark it as visited and then go through the neighbors, make sure that the neighbor is unvisited before you go there. And finally, don't forget to call your recursive function after you finish implementing the function. Okay, so that's it for DFS. Now let's talk about the BFS, so the breadth first search. So,
and sorry, just to quickly interrupt, the workshop code is sent. Oh, whoops, let me send it again. The workshop code is sent in the chat. If you want to earn points for attending this workshop, please put in the code. Thanks.
Okay, so for BFS, let's review the process. So again, we're initializing the. So first we need to import the queue, and then we need to once we've created it, we can add starting node. Again, you don't have to start at node 1, obviously, and I'm just picking node 1. And you can mark node 1 as visited. Put it into the queue. And I think I'll post this entire thing onto the document after I'm done commenting it. Okay, so here we're just making sure while there are visited nodes. Right, so we're going to go until we have no unvisited nodes left, which means we've traversed the entire graph. We're going to extract the next node to go to. So, and we're going to name that U, right? So we're printing, okay, we're visiting node U right now. And we again loop through neighbors. Make sure it's visited. And we, first of all, we put it into the queue, put the queue. And then we're going to mark the neighbor visited. And remember, we're doing this because to avoid having duplicates. Okay, so let's try running that. Oh, I already ran the code. So okay, so what I did was I should have done this for the DFS as well, but I'm just going to look at the output here and look at, okay, it doesn't let me copy the output. Okay, so this is what we get as the output. So we look at the output compared to the graph. So we started from node 1, visited node 4, then visited node 2 and 3 before visiting node 7, because node 7 is a distance of 2, while we're actually, these are all distances of 2 from 1. So it's going to visit 2, 3, and 7 in some order. And then it's going to visit node 6. And before visiting node 5, it's going to visit node 8 because that's closer. So from 7, 8 is closer than 5. And so on. And so we're visiting node 10, node 5, which is right there, node 9, which is right here, 11 and 12. So you'll notice that we're traversing the closest nodes first, and then we're going out and expanding it to further nodes. And this idea is going to be useful to us later. Okay, so any questions about BFS so far? Okay, I'll go on to take up exercise 3, which is the, I would say, most challenging exercise out of these. So let's first, before we start looking at the implementation, let's understand the idea of how we can do this. So we're asking the user to input 2 nodes, and we want to output the minimum number of edges between these 2 nodes. And this is more challenging because we're asked to minimize the number of edges. So it's not enough to print any path, but it has to be the minimum distance. So for example, if I were to choose something like 1 and 8, well, there are multiple paths to go from 1 to 8. So I can go from 1 to 4 to 7 and 8. And I can go from 1 to 4 to 7 to 10 to 9 to 8, right? So So we know that we're going to use one of DFS or BFS to do this because that's what we taught in this workshop, right? So let's consider DFS first. So if I went and performed DFS, I could go from 1 to 4, then 2, then 3, then 7, then 6, then 5, then 7, then 10, then 11, then 12, then 9 to 8. So then what I've really done here is in the call to 7, I've visited 8, right? So it would depend on whether it would depend on the order in which 8 and 10 are stored in the adjacency list of 7. So it's not guaranteed in DFS. Just to illustrate, I could go here and I could go here, but from here I can either go directly there, but it's also possible for DFS to take this detour here and end up at 8 using a longer path, right? So in this path, I would say the distance is 1, 2, 3 edges versus a path of 1, 2, 3, 4, 5 as edges. So clearly this path is better, but just one DFS like from the source to visit all the nodes, it's difficult for you to know that whether DFS took the optimal route or the suboptimal route, right? So we don't want DFS to take this kind of detour. So I'm not saying it's not possible with DFS, it is possible, but it's a lot less intuitive and just harder to implement in general. And if we consider BFS, we'll see that BFS is the natural choice when we're solving this exercise 3. So let's label, again, let's label the, or actually, let's just start the BFS from 1. So first it's going to go to 4. Then it's going to visit 2, 7, or 3 in some order, like this. So then after visiting these 3, it's going to visit 6 and 10 in some order, right? And then it's going to visit 5, or sorry, after visiting 7, it's going to visit 6, 8, and 10 in some order, right? So if I were to choose 1 and 8, then this path would already be established right here. There's no way that we're going to go to 10, then to 9, then to 8 before we go directly to 8. And why is that? Well, we talked before that the closest the node is to the starting node, so the starting node is 1, the closer the node is to the starting node, the earlier it will be visited. And so that means that the first time we visit the node, that will be okay, if we visit one node before another node, so if we visit 8 before we visit node 10 or node 9, node 10, but node 9, so we visit node 8 before we visit node 9, then that means node 8 is closer to 1 than 9. And we can use this property to then find the distance from the source to all the other nodes. So what we're going to do is define an array dist. So dist at u is going to store the distance from 1 to u if we're starting at 1. So I'll write this down somewhere. So we're going to let this at u store so if we have this array, so first of all, initially this at u is infinity. So there's infinity in Python. What you can do for that is either use a very, very large number, like just 1 with a bunch of zeros behind it, or some like a string long number with just 9s, or you can just from math import inf, and this will represent infinity in this case. So if you use this, then anything you compare with infinity will be less than infinity. So you can think of it that way. And so initially, we're going to set this at u to infinity. And the only thing we know is that this at the starting node, which is 1, is equal to 0. Right? Okay. So let's go back to our graph. So let's imagine our traversal again. So I'm going to I'm going to zoom in a little bit. Okay, so let's start at 1, where dist at 1 is equal to 0. And I'm just going to write the distance right here. And if I don't write any distances, assume that it's infinity. So let's visit the neighbors of 1. So this is 4 is a neighbor of 1. And we know that to go to a neighbor, we must be traveling through an edge, right? We must be traveling through this edge right here. So that means that the distance must be increased by 1. So the distance from 1 to 4 is 1, because we're traveling on an edge. And now we visit the neighbors of 4 that are not already visited. So 1 is visited. So from 4, we can go to 2, to 3, or to 7. And now each time we go on to an edge, we're increasing again the distance by 1. So when we go to 2, the distance will be 1 plus 1, so that's 2. So relative to 4, it's going to be 1 further away from 1. Now, if there was an edge from 1 to 2, which would make the distance from 1 to 2 1, then it wouldn't be possible for us. Actually, it would mean that we would instead look at 2 from 1 and realize that 2 is 0 plus 1, right? But since there isn't such an edge, we don't have to worry about that case. So 2 is just going from 4, so 1 plus 1 is 2. And the same case with 3. So 2, 3, and 7, you'll see that they're all 1 edge away from 4, and they will all be equal to 2. Okay, so you might ask, why aren't we updating 1? And that's a good observation, because if we look at 1, that's also 1 edge away from 4, right? So what we have to do in our implementation is to make sure that the distance that we're updating isn't already smaller than this distance plus 1. And which means that the node that we came from will never go back to it, because the distance must be smaller, right? And that's using, again, the property of, if you visited that node before this node, it's at least as close as you. The earlier you visit a node, the closer it is to the source. Yeah. So now from 2, we visit the neighbors, and they're all 1 edge away. So if 7 has a distance of 2, then these have a distance of 3. And if 6 has a distance of 3, then 5 has a distance of 4. It's just adding 1, right? Because it's 1 edge away, and this is 1 edge away. So 3, looking at 9, that's 4, right? And now from 9, actually, well, if you pretended you were on 9 and you looked at 10, you wouldn't be updating 10 to 4 plus 1, because that value is already smaller, right? So this edge right here, it wouldn't, either of these would update these to a 4, but this 4 won't be negatively affecting these by assigning it a worse distance or a greater distance, let's say. So we have to do a check to see that the distance isn't already smaller than the current distance. Okay, so from 3, again, they're all 1 edge away. So this will be the distance of 4 and the distance of 4. And we can verify all of these locations. So from 0, from 1 going to 12, let's say, we would go through this edge, go through this edge, go through this edge, go through this edge. So that would give us a distance of 4. This won't quite work with DFS, because you might go from 1 to 4 to 7 to 8 to 9 to 10 to 12, right? So that when you do DFS, it's unsure whether you'll actually go on the best path. But using the properties of BFS, we can solve the shortest path problem on the unweighted graphs. Okay, are there any questions about how we solved exercise 3 on paper here? Okay, okay, so I think looking at the implementation might also help you understand. So First of all, we're just going to ask for 2 nodes. And then we're going to import infinity. And then we're going to initialize this. Okay, I can write down some of what I said. So if there is an edge u to v, then this at v is at least as good as this at u plus 1. Since you are, since there's an edge between them, right? There's only one edge, so you're adding 1. Okay, so q is equal to q. So again, we're creating in the starting. And the distance to, like, from the starting node to the starting node, this is 0, right? So from 1 to 1, there's no edges that are needed. So distance is 0 at first. So while no nodes are unvisited, while there are unvisited nodes, we extract from the node, or extract, and then we go through its neighbors. So again, we're doing this check of, okay, is the distance of v going to be improved if we use this edge? Or sorry, if we use the current node? In some cases it will. So going from 7, if we go to 8, this before it was updated to 3, it was infinity, right? That's what we initialized it as. We realized that 2 plus 1 is smaller than infinity, so we reset this distance to 2 plus 1. Now, if we look at 4 instead, 4 has a value of 1 when it got to 7. So 2 plus 1 is greater than 4, or sorry, 2 plus 1 is greater than 1, which is the distance to 4. So what that means is we're not going to put 4 into the queue, and we're not going to update its distance. And so you can see that since our distance is always accumulating, we don't need a visited list anymore. All we need is this check of the distances from the source. So then if the distance at the other node is greater than the current node plus 1, so if going through this node actually helps its distance, then we, first of all, we reset its distance. So that's almost like marking it as visited already. And then we put this node into the queue. And so this process is very similar to the BFS process as well. And finally, we're going to print the minimum distance. So let me type in the input again. I'm pretty sure I typed in something wrong. Okay, and we want to find the distance from 1 to 12. Or actually, we already did that one. Maybe I can pick a different one. Maybe from 5 to 11. Maybe that, or yeah, sure, from 5 to 11. Or actually, since we started from 1 on this graph, I want to pick something from 1. So maybe 1 to 8 would be an idea, or 1 to 9. So 1, 9. Okay, what happened here? Oh, whoops. Okay, so since I commented this out, Q was not imported yet. So let's import the Q. Yeah, that's fine. we want from 1 to 9. So 1. And the minimum distance is 4. And let's check to make sure this is correct. So from 1, we can go to 4, 7, 10, 9, and that would be 1, 2, 3, 4 edges. And let's try another way to see if it's faster. So from 1, we go 4 to go to 7, to go to 7 to go to 8, then go to 9. So this is 1, 2, 3, 4 edges. So 4 edges is indeed the minimum distance from 1 to go to 9. Okay, so are there any questions about anything we learned today, since it is already 5 o'clock? Okay, if not, thank you for coming to the workshop. It is 5 o'clock, so I'm going to end the meeting here and enjoy the rest of JumpStart and MasseyHacks.